to start off our celebration, I have the honor of introducing the president of Bell Labs and Nokia CTO, Marcus Weldon.
It's fantastic you can be here today. I see this sort of as Bell Labs as a place, as being a place that birthed the information age. And you all are contributors to that, either in the past, the present, and the future. So we're going to explore that today.
I decided communications information theory was indeed the right direction to go. That led to ultimately my doctoral thesis, which was connectivity and probabilistic graphs. And in looking into that and doing the background research, what did I find but a key paper on reliability using unreliable components, at that time I think relays, that was written by Claude and had a lot of excellent mathematics, etc., and so helped me in putting together my own thesis.
So I invented Ethernet, but only for certain values of I had invented an Ethernet. So there's a lot of controversy about these three things. So Dave Boggs and I built the first one. But anyway, let's talk about the innovation associated with that. For those of you who don't know, Ethernet is the plumbing of the internet. It's way down here, and there's all that other stuff way up there that's much more fun and interesting. Other people, someone in this room, had all that fun up there with. But occasionally we get our moments. So one day Steve Jobs called me and he invited me to the premiere of Toy Story at De Anza College, the big Pixar film. He sent a limo to my house, a plumber. You know, Steve is way up there and I'm way down here. I went to the debut. Of course, Toy Story was wonderful. They had a red carpet. Steve hired photographers to pretend to take pictures of us so that we would seem to be important. And on the way out, I shook hands with Steve and I said, you know, Steve, I want you to know that every bit of that beautiful movie you made was carried on Ethernet. And Steve just turned to me and he said, thank you. And I've been living on that positive reinforcement ever since.
The thing that is interesting to me most about Bell Labs is not Bell Labs, but the fact that Bell Labs is a gem with millions of houses around it. And that helps me understand how extraordinarily rare and how extraordinarily special innovation and the kind of people that are attracted to work here, now, and in the past. And that is what I want to talk today about the role of people and AI and innovation. When I was here as a summer student, right? So thank you very much. It's part of the 1127 group where we did Unix and C, where we pioneered open sourcing. And pretty much everything that you use when you're on the internet today started here. Because the ideas around the operating systems, languages, all of the services were literally built on the 6th floor around the corner. And I remember it extremely well. When I was here, I didn't know anything. I was, very young. I didn't know about the internet, right? I didn't know about the personal computer, the smartphone, the GPS, none of which had been invented. I didn't know about Uber and Google and Facebook. My camera used film, and my phone was the old kind, right? That was the world. But what I did know was that incredibly smart teams could assemble to make things that would change everything. And I want to talk about the role of teams and how important that is, because that's sort of what we're trying to do here in the new Bell Labs. And I also didn't know how to predict the future. Bob talked wonderfully about sort of doing these diagrams of the future and platforms and so forth. I didn't even understand that. But what I did know is that to predict the future, you have to think about strategy and you have to be disagreeable. Now, what do you mean by disagreeable? You have to disagree. You have to challenge assumptions. Innovation is about taking a position that's contrary to the common orthodoxy.
We're all cyborgs. Like every time you interact with a piece of technology, you're in a human-computer interface. We've been extending our capabilities into physical tools for a long time. A hammer is an extension of your fist, a knife is an extension of your tooth, and starting with writing and cave paintings, we've also been extending our mental selves into these new tools. And those tools have been fundamentally unstable. What was originally the size of a gymnasium is now, as you know, very small. We now, instead of having many people to one computer, we now have many computers to one person. So today I'm going to talk about this idea of calm technology, which I got from the time machine of Xerox PARC. So let's talk about designing calm technology. How can we design things that make better use of our attention? So I made a few principles and kind of put them with Mark Weiser and John Seeley Brown's principles to kind of make a small framework. And this is not necessarily aimed at you. It's aimed at a lot of people who keep trying to make these things without understanding that there's a history behind them. So technology shouldn't be requiring all of our attention, just some of it, and only when necessary. And you have to design that incredibly well to make sure that that works.
It's a great pleasure and honor to be here, because information theory is probably the only reason why it's going to be possible to understand the brain. Now, to explain why I say that and what I mean by that, I'm going to try and take you behind the scenes to how we think about the challenge of building a biologically accurate digital copy of the brain. So, if you had to walk down the street and you didn't know that information theory was lying at the heart of understanding the brain, and somebody came up to you and they said, I'm going to build a digital copy of the brain, your first reaction would be to say, you're crazy. We don't know enough about the brain. Why don't you build a digital copy of a worm's brain with 302 neurons, or a snail's brain with 10,000 neurons, or an ant's brain with 250,000 neurons? The answer is that it's irrelevant how many neurons there are, how many synapses there are. The only thing that is relevant is the order in the system. And as information theoreticians, you'll begin to see where this is going to.
This is really one of the few cases in science where a whole discipline comes out of the blue. And obviously, Shannon, worked on this, as you saw from that letter from Princeton. He had worked on this for more than 8 years. So, there's always the perennial choice. You do either abstract, pure mathematics that really has very little bearing to practice, or you do applied mathematics that is useful but kind of messy. All right. Well, faced with that disjuncture, actually what Claude did was elegant mathematics that was extremely practical.
So we're going to have some fun now, continuing some of the insight into the man, Claude Shannon. And I'm going to be joined not only by Sergio, but 3 other panelists who I'd like to invite up now.
What Claude did was something brilliant intellectually. It didn't lead to a company. Only other people had it lead to a company. He wasn't really interested in companies. He was interested in intellectual puzzles. He was interested in solving those intellectual puzzles. And the question was, how did he do this? He was very bright, as everybody has pointed out, but was he brighter than anybody else? I've seen an awful lot of bright people. They're very, very smart, but what was it about him? He once gave a talk while he was still at Bell Labs, I believe, where he was trying to describe what it was that he thought was needed to be a creative person. And I've been studying all my life to try to figure out what his tricks were. And what he said, the first part of it wasn't very interesting. He said what it requires to be creative is first you have to have education. You have to have experience, education and experience together. You can't be a creative person just bombing off and doing something. You need to learn something first. You need to be very smart. Well, that's no surprise about that. But then he said the third thing you need, he called it motivation. I think most of us today would call it curiosity. You have to have a burning curiosity to understand something that you're trying to work on, that you're trying to understand.
So as Araj mentioned, we're going to move into the student competition portion. What we did was we put out a call for papers on new projects from newly minted either graduates or PhDs or about to be PhDs. We got around 50 proposals relating to information theory. We're going to have presentations from 3 of the finalists. I'd like to bring up Navid as our first presenter.
Today I'm going to talk about an important trend that's expected to play an important role in future wireless networks. And this is in fact the trend that I'm mentioning here, in which the regular communication between the cellular base stations and users in uplink and downlink is going to be replaced by the communication between devices directly, which is known as device-to-device or D2D communication. So in such a setting, we have used some tools from information theory to refine the conventional thinking that's being used in this area. And in particular, if you look at the network like this with a bunch of transmitter-receiver pairs, you can look at this as an interference channel whose capacity region is still open. But people have been trying to come up with some engineering criteria for improving the performance of such networks, especially, for example, coming up with metrics for scheduling links in such networks. And we have taken a step further to introduce a theoretically justified criterion for link scheduling in these networks, which outperforms the existing ones that I will mention in a minute. So the message is that information theory can reveal many untapped resources in a wireless network.
So in the true spirit of this conference, this project really starts with Shannon, and in particular with Shannon's ideas on redundancy. So we know from information theory that we have a pretty mature idea of how we can remove redundancy from information and also how we can add redundancy back into data so that the messages we transmit can be robust to noise. Now, what we want to do here is to sort of take these classical ideas about redundancy and apply them into a whole new domain. So instead of exploring information like Shannon did, what we want to do is to explore redundancy when it is added to physical objects.
The problem I'm talking about is that Riedmüller codes achieve capacity over erasure channels under optimal decoding. This is actually a pretty old conjecture in coding theory. And perhaps what's even nicer about this work is that the proof technique that we use is very general, and it applies to codes that have enough symmetry. So actually this topic was, Sergio Verdu was talking about this at the end of the Fireside talk, so I actually thank for him. And he was saying that, I mean, at the beginning, some codes essentially Shannon introduced random codes, and then people were using mainly codes with structure because they were easier to encode and decode. But no results were available on proving their asymptotic optimality. So essentially our results is, let's say, first leap in this direction.
So this is our tribute to Claude Shannon, but it's just testament to what a profoundly impactful man he was. There's the milestone plaque. And then behind you, when we turn and look at Eric, that thing behind you, which we built on the remnants of an old building, is the Shannon Amphitheater. We will be regularly holding events here. Performers, some of the art and technology events you're going to see later tonight will be hosted here, and out there will be a place where people can exchange information, exchange art, witness art, but that's going to be our testament to Shannon beyond the plaque. So Shannon Amphitheater, we are going to hereby announce. In fact, Martin Carroll had the idea of putting it on maps, so it'll be seen when everyone looks up a Google map, it'll say Shannon Amphitheater, and here is going to be the Shannon milestone plaque. So without further ado, okay, here we go. This is our ode to our pièce to Claude Shannon. well done. Very Shannon-esque. So thanks, everyone. If you've got champagne, let's do the toast. Turn around and look at Eric. That way. To Claude. We're here to honor Claude Shannon. Claude Shannon was the father of what's called information theory. And it's a very interesting theory because it actually allowed us to know how much information you could transmit over a channel of any type. So what we're really doing today is expressing the network through art, and conversely, art is using the network to be better expressed. You're going to see a tap dancer who actually allows Shannon to speak. So when that movement happens, he's creating Shannon's voice. You're going to see a pianist whose hands are tracked, and every movement measured and connected to things that happen in the tent. You are going to see the Voda played for the first time in a very long time. And of course, you are going to change the experience.
It is first necessary to represent the various elements involved in mathematical entities, suitably idealized from their physical counterparts. We may roughly classify communication systems into three main categories: discrete, continuous, and mixed.
And the information age was born.
The position of your phones will be captured by our human digital orchestra. You'll see your phones changing color. There are signals from the music being sent to you to change the colors on your screen. I see the dots of all the phones. We've achieved synchronicity. You are the human digital orchestra.
We are both at an opportunity and at a challenge. As the number of devices increases, these fundamental limits of how much information can travel through space by whatever mechanism are becoming more critical. At the same time, I think that there's a lot of opportunity there, both in terms of figuring out how to do that communication properly, as well as helping fields understand other kinds of communications that happen in nature, for example. Bringing our tools to bear on the kinds of questions that people study, for example, in biological systems, but without the kinds of tools that we have an opportunity to apply there. So I think that there's a great opportunity right now.
Yeah, I might just add by amplifying something you said is that, Shannon's ideas are really so visionary that, as I said earlier, 70 years later, we're still using the basic concepts and in ways that I'm sure he never envisioned, So I suspect that, as Michelle said, we're going to continue to be able to use his ideas to help us understand the limits, regardless of what regime we're in.
Unlike just not that remote future, where the problem was how to do things, what to do. It's clear. I want an FM transmitter, FM receiver, if we mention World War II. How do I implement it with the radio? Well, no transistor. How? That was the problem. Today, it's just the opposite. What to do? So theory becomes much more important. And information theory not only gives you the way of what to do, but what is optimal to do, and sometimes even says how to do it.
But as we'll see, and as very much as we have seen with Shlomo, this is going to be about matrices and reloading them and just considering them differently. All right, so Shannon gave us a lot of things, as we just all heard. But one of the things I want to talk about, because this will just be the context for this reloading of the matrix, is the point-to-point channel, which we saw in the talk by Vince and Michelle, which is in effect this combination of the source coding and the channel coding with one receiver, one sender. And what happens is the source coding is removing redundancy for efficient storage. The channel coding is introducing redundancy not out of vice, but for the purpose of allowing redundancy. And there is separation between the two. And what we mean by there is separation, but what I want to be talking about in the rest of the talk is going to be sort of growing this matrix in growing from a vector in effect into a bigger matrix, which is to consider the entire network. So what we have is a point-to-point model, and we'll see that this point-to-point model, in effect, and this was foreshadowed very much in Shlomo's talk, is just a generalization, can just be generalized very readily to a full network.
And the hope is that we will not stop trying to find exciting applications for coding theory. I am a coding theorist, I'm not an information theorist, but I can tell you that the excitement for coding theory in experimental design and in synthetic biology is exceptional. Just before coming here, I was at Washington, D.C., attending a huge panel and meeting of all the major players in synthetic biology with the goal of establishing a new field where we can do basically DNA computing, DNA storage. And 3 topics were discussed, 3 topics that were deemed as very important: DNA synthesis, DNA sequencing, and coding.
So today, I'm gonna talk about fiber communication. The title of this talk is Information Theory Meets Optical Physics. And so I'm going to talk essentially what's called a nonlinear fiber limit. 99% of the data traffic for long haul goes to optical fiber. So we can really say that optical fiber is the backbone of the internet. And what is surprising, actually, is that we don't really know the capacity limit of fibers. And when we asked this question about 15 years ago, there was no good answer to that question. And it's hard to argue that fiber is not among the most important communication media. So the main reason I think this is the case is that you have fiber is a nonlinear medium. So basically, as you increase the power, the fiber itself, the glass, changes properties.
Let me begin by just explaining how I ever happened to think of bringing information theory into economics. It's a little random. As an undergraduate, I was a math major and wrote my undergraduate senior thesis extending Shannon's coding theorem as it was displayed for finite memory channels in Kinchin's little book to infinite memory. And then I forgot about information theory and went into economics. And then about 10 years or so ago, 10 or 15 years or so ago, I was struggling to critique all the ways economists have found to introduce inertia into models of economic behavior, which all seemed very ad hoc to me. And it occurred to me to add an appendix to one of my papers on that, saying, maybe we could explain some of this with information theory. And it's turned out to be a fruitful direction, and now there are many other people in economics working in this area.
So this conference is about history, so start with a little bit of history. As we know, in 1948, Claude Shannon wrote his paper in which he invented a mathematical theory of communication. 70 years later, all communication systems are designed based on the principles of that theory. So to me, that is an extreme example of an unreasonable effectiveness of theory, right? How can an abstract mathematical theory have such a wide impact on the real world? However, today I want to dig a little bit deeper, and I want to talk about the unreasonable effectiveness of this particular theory. And the observation, which has been made before, is the following. Shannon looked at the problem of information limits without computational complexity consideration at all. Yet, 60 years later, after a lot of research, which was described on these 2 days of conference, ultimately revealed computationally efficient coding schemes that achieve these limits. So that, to me, is sort of in the core of the matter, the unreasonable effectiveness. That is, Shannon never considered computational issue. So why would there be solutions that are computationally effective?
What is the fundamental limit of clustering? And that's, of course, the connection for us with Shannon. So here is the goal now in the next slide is, can we Shannonize data clustering? So what do I mean by the Shannonization? So of course, there's a few points that were already mentioned throughout the workshop. The first one is get a good toy model. That's what Bob Geiger said yesterday, simplify the problem. In the case of communication, this was a discrete memories channel in the paper of Shannon. The second part is derive the fundamental limit without focusing upfront on the efficiency of algorithm. Using the information that there is in the graph, when can you recover those communities? So in the case of Shannon, this became the channel capacity, this fundamental limit. And now the third point is, now that we have a target, which we didn't have before, can we achieve that target with efficient algorithm? Which, of course, in data transmission was far from an easy task and took a lot of years, but eventually got resolved. And then, as Geiger said yesterday, you can add layers, generalize, and iterate that process.
The title of this panel is, Shannon Theory 50 Years from now. So I have with us Emre Telatar, EPFL, Andrea Goldsmith, Stanford, Rudy Urbanki, EPFL, Gerhard Kramer, TU München, and Olan Orlitsky, UCSD. All of them also have put in significant time in the past at Bell Labs. Everyone has made notable contributions to information theory.
Go ahead.
Go ahead.
Well, I think our community has been very successful over the last, as we said, 70 years, and has contributed a lot to communication fields. And I think now it's maybe time for us to diversify a little bit and consider other fields that people have done so before. And I think we have the tools, we have the information, we have the people, and I think we just need to focus a little bit more on it. And I think we'll continue to be successful for many more years. Let me maybe continue along the line what Alon said. I think our students and our education, I think it's a fantastic basis, and there are great opportunities out there for the obvious reasons. Machine learning, I think, is ripe for, it's an extremely interesting area, has lots of application, but I think it's ripe for someone to come along like Shannon to explain, for example, why deep neural networks work, and I think we would be very well positioned to play a role in that. And there are many other ones, I think, where we could play a similar role.
Two quick comments. One is thanks to Marcus and to everyone for putting this on. My 2 summers at Bell Labs were some of the most influential time of my entire career, and I hope that Bell Labs from those days is going to re-emerge and actually be even stronger. So this event seems to indicate that, so I was happy to see that. And then one other comment that no one's made is that the information theory community is a very special community. It's very tight-knit. Some of my dearest friends are from this community, and I think that creating a community like that where you feel that it's a professional home for your entire career and that you really enjoy your collaborators and the people you work with and the people that you see at these kinds of events is one of the things that has kept our field vibrant and attracting the most the best minds in the field. So I hope that that will continue along with the relevance of the field.
Let's thank the panel. Thank you. It's been a pleasure. Thanks.
I've realized I'm an information society groupie. Because essentially, it seems to me from having listened to all the talks, that's what your community is, nearly every aspect of that. And I reflected on a few things to show how you sort of embody that in a perfect way. One is I learned that you love both point-to-point connections and networks. You love fundamental things, but you like to be practical too. You're ambitious, but you're modest. I think that was very much part of the Shannon aesthetic. Expansive, but cautiously so, because you have to apply those other principles, it has to be rigorous. You are inclusive and not exclusive. As a community, I think it's very impressive how you welcome others as long as they apply the appropriate standards. It doesn't matter who they are, where they came from, they just have to apply the standards of rigor. But you also allow sort of leaps, the leaps of Shannon without waiting to prove things, because you know it to be true. I think that's wonderful. Young and old. It's not a field of one generation and with no follow-on generation. It's a field of young and old. Male and female, quite rare, actually, in our STEM areas to see as many women at the top of the field as men. It's both industrial and academic. It's serious and humorous. So in my summary, I would just say it's the essence of both Claude Shannon, and Claude was the essence of Bell Labs, and I don't think there's any better ending than to say that. It's been a wonderful, wonderful time. So I will just reiterate, the only payment you have to give for this is to send us your best and brightest students. You're allowed to keep a few for yourselves, so we have an active collaboration between us and you. But thank you all very much. It's been an incredible occasion. Bye for now.